Here's the analysis for the lab on determining the molar volume of a gas, hydrogen gas. So we had our data. That was all collected in the video that showed you the reaction between magnesium and hydrochloric acid to produce the bubbles of hydrogen gas that fill up the eudiometer. Maybe not all the way, but most of it was filled with gas. We had the mass of the magnesium strip, the final volume of hydrogen collected. The barometric pressure was just like the atmospheric room pressure at the time. That's just something that you'll look up. You don't have to really measure that. In the AP equation packet, they will kind of remind you that millimeters of mercury are equivalent to a torr. So either of those units can be used interchangeably. And then finally, we eventually want the temperature of the hydrogen gas, but the nearest thing to the hydrogen was the water. And so we could easily take the temperature of the surrounding water, and then we're going to make a little assumption that because the gas was in direct contact with the water, they were probably at the same temperature. Okay, so in a nutshell, here's what we had inside of the eudiometer. So here's my eudiometer. We had the string. It had a little coil of magnesium. There was like a rubber stopper then. Maybe, I don't know, kind of like that. So to hold the magnesium string in place, and there was a hole in the stopper to let the water and magnesium chloride solution produced out of the big tube. As the reaction occurred, then eventually we had most of the tube filled with hydrogen gas, but there was still a little bit of liquid in the tube. Mostly water, but probably a little bit of excess hydrochloric acid. We purposely probably used a little extra acid, but we wanted to make sure that the entire piece of magnesium was reacted. That was my limiting reactant. Okay, so eventually then we had bubbles of hydrogen gas that fill this eudiometer. Yikes! Okay, so that's crazy. That's all going to be hydrogen, H2 gas. Awesome. The problem is that I think we mentioned that often this is called wet gas. When you collect a gas by water displacement, you've always got this one problem here. And it's just that water vapor tends to form naturally from the particles on the surface of the water layer. So some of these little water molecules are also going to decide, I want to go into the gas phase as well. Now there's not a lot of water vapor up here, but there's a little bit. H2O, a little bit will be in the gas phase. And eventually I want to know just the pressure of the hydrogen gas in that tube. So we need to do this little correction using Dalton's law of partial pressure. It's going to look kind of like this. The total pressure in this eudiometer tube is equal to the pressure of the hydrogen gas plus the pressure of the water vapor. So this Dalton's law of partial pressure is really simple in concept. It's just that when you have a mixture of gases, the total pressure is the sum of the pressure from each gas. And so we've got two gases in that upper compartment. Up in here, there's going to be a mixture of water vapor and hydrogen. So we need to correct for the pressure of the water vapor. We want to subtract it off. Okay, so first, what's the total pressure? It's the barometric pressure. The total pressure is the total pressure in the room, or the atmospheric pressure that's being applied to this system. It's the 746.76 millimeters of mercury. Now, if this were like a free response question, that would be given to you. That's not something that you would calculate. You would have to be told what the lab conditions were. I want to solve for the pressure of the hydrogen gas. The pressure of the water vapor is kind of a constant. That's something that you can look up on a chart. You just have to know the temperature. So our water temperature was actually a little bit funky. What did we have? About 22.7 degrees Celsius? So our water vapor pressure is going to be like somewhere in here. So I noticed this prior that, oh gosh, like this table here is going to be a little bit funky in that we're like in between these two. And so I kind of did some math to figure out where about 22.7 would fall. And it's probably somewhere around, let's see, what did I get? About 20.7 millimeters of mercury. And that would be at the 22.7 degrees Celsius. This would also be something that you would have to be given. If this were in a free response question, you would be given the water vapor pressure. Because again, that's a constant. Or you would just be given a chart like this. And if they said my water was at 19 degrees, well, we're assuming then that we can just look up the vapor pressure on the chart, and we'll now subtract that from the total pressure. So I've got about 20.7 millimeters of mercury coming from the water, 20.7. And all I have to do is subtract. So it's a really simple correction. It's just a subtraction. But it's always the first step when you've collected a gas by water displacement. The total pressure in the lab room would be given to you, and that's a sum of the pressure coming from both gases in the tube. I only want to solve for the pressure of the hydrogen, so we need to subtract off the water vapor pressure, which you're either given or you look it up on a chart. So I'm going to say then, thanks, I'm running out of space. I'll kind of put it up here. That the pressure of the hydrogen alone, let's see, would be about 726.06 millimeters of mercury. There we go. Awesome. Easy. Step 1. Step 2. Calculate the moles of hydrogen that should be formed from this reaction. But it would be helpful to have the reaction. Okay, so we have magnesium reacting with hydrochloric acid, or HCl. Now eventually we'll go through the different types of reactions and balancing equations, and often they're just given to you as well. But this might look familiar to you. It's one of those single replacements where magnesium is normally a +2 ion, hydrogen is +1, chlorine is -1. So my single element is the magnesium, and it'll replace the other positive ion in the HCl. So you switch a positive for a positive or a negative for a negative. So since my magnesium is positive, it can switch with the other positive. Now that's going to kick out the hydrogen, and on its own it's going to be that diatomic hydrogen gas. Then magnesium will come in and bond with the chlorine. And here's why you have to go like charges in your replacement. Because when I make a new product, if it's an ionic product, it's got to have a positive ion and a negative ion. So I've got to switch a positive for positive or a negative for a negative. Now I just balance out this formula, make it neutral with 2 chlorine ions. And then finally, you may remember balancing equations last year, right? Where I'm just going to work this side to side and make sure I've got the same number of magnesium on both sides, 1 and 1. I want the same number of hydrogen on both sides, 2 and 2. And perfect! That gives me 2 chlorine on each side, just what I wanted. So we do want to look at this in terms of a little stoichiometry, and I need to have the balanced equation then, mainly so I know the ratios. Calculate the moles of hydrogen that should be formed from this reaction. Oh my gosh, it feels like forever since we've done stoichiometry. So we kind of mentioned that the limiting reactant is the magnesium. It was totally consumed. It's gone. The HCl was in excess, which is fine. We just used a little excess to make sure we completely consumed the magnesium piece. Okay, so then I'm going to go from my magnesium, and I'm looking for moles of hydrogen. I'm going to compare moles of magnesium to moles of hydrogen. It's a 1-to-1 ratio in my balanced equation, but it does mean that I need to figure out how many moles of magnesium I would have had then. And so that's where we'll start with the 0.061 grams of magnesium. We've got to turn that into moles. So we'll cancel grams of magnesium, turn it into moles of magnesium. I should make those uppercase. That'll just look a little nicer, right? Magnesium. There we go. Looking on a periodic table, 1 mole of magnesium is about 24.30 grams. Now technically then, if I cancel my units, grams and grams are gone, and I'm at moles of magnesium. And right there, maybe then you can say, oh, it's a 1-to-1 ratio between the magnesium and the hydrogen. And you'd be right. Now obviously you can put it down if you want. Then technically, now that I'm in moles, I can cancel moles of magnesium, and I can switch it to moles of anything else. I want the hydrogen. And that's where I plug in my 1-to-1 ratio, and yeah, it's not going to change anything. Moles of magnesium will cancel, but it just makes me feel good, right? I got the stoichiometry set up, and we're going to plug this in our calculator. It's gonna be tiny. And I guess technically my 0.061 is 2 sig figs, but I don't know, I'm just gonna leave 3. I don't want to lose too much precision because this is a really tiny number. 251. And that would be moles of hydrogen. That's the moles of hydrogen that should be formed from a 0.061 gram strip of magnesium. That felt really good. Stoichiometry, I have missed you. All right, we got question 1, we got question 2, 3. We are using the ideal gas law. The ideal gas law is Pförtner. Pförtner is in your AP equation packet. It's in the section on the very back page called Gases, Liquids, and Solutions. It's in there for you. It's the first equation. So you don't have to memorize it, just know how to use it. We want to calculate the theoretical volume of hydrogen that should have been collected under lab conditions.
You should now be in homeroom.
So,
Thank you.
if I'm supposed to produce 0.00251 moles of hydrogen, then what volume would that be under my lab conditions? So we're going to plug in all the conditions of the lab and solve for volume. The volume of hydrogen that should have been produced. So in the lab, the corrected pressure is just your answer from number 1. The pressure of the gas should have been from number 1, 726.06 millimeters of mercury. So I'll make a little note. That was from number 1. That was the pressure of the hydrogen gas alone in the lab. V, my volume, will stay the variable. N stands for number of moles. 0.00251. Now R. R is the gas constant. And when you look in your equation packet, you'll find the value of R. It says gas constant R. So you don't have to memorize them, just look them up. But word of caution, in the packet there are 3 versions of R. There's one that looks like this. So there's an 8.314. And then in the packet it looks like joule, and then it's got moles to the negative first, Kelvin to the negative first. It's like joules per mole Kelvin. There's one that's 0.08206. And then that one says liter atmosphere. And then, oh gosh, mole -1. Let's move this guy. There we go. Kelvin, -1. Okay, so that's in the packet. And then there's this guy, 62.36 liter liter, in the packet it says liter torr. I'll put that in there. Liter torr. And then mole to the negative first, Kelvin to the negative first. Okay, so here's what I wanted to mention. When you're looking for a version of R, this is not the one you're going to use with gases. Now it's kind of weird because it says R, gas constant. Not this guy yet. This one that's got joules in there, we will use it, but we'll use that a lot later when we're also bringing in like some thermochemistry and like heat transfers. Then we'll use the one with joules. Now you want the one that's either got like atmosphere or torr. And all of these other units are the units that you need for perv-nert. Like perv-nert has volume and it's got to be in liters. Perv-nert has pressure. It can either be atmospheres, torr, or in the packet they'll tell you that torr is the same as a millimeter of mercury. These are equivalent. N stands for moles and T is temperature. It's just going to need to be in Kelvin. So for now, when you're doing gas laws with perv-nert, you're not going to use this guy, sad face. That looks like a mustache. You're going to use one of these. Or this guy. Use the one that has a pressure unit in. And in fact, that's usually how you'll choose between those second two. The second equation or the third, the second version of R or the third. Look at what pressure unit you're using and then choose the appropriate version of R. Now if it doesn't specify, then pick either of them. But just know that like if you were solving for pressure, you know, if you use the 62.36, your pressure is going to come out in torr or millimeters of mercury. If you use the 0.08206, your pressure would come out in atmospheres. Awesome. So the other thing that I have to just be careful of with perv-nert is just that all of the units in my work need to match the units of the constant. So here we're solving for volume. It's going to come out in liters. I've got moles, I've got R, then I'm going to use the version of R that's the 62.36. And then T, or temperature, must be in Kelvin. And they'll tell you in the packet, it's in this same section. They'll give you the conversion from Celsius to Kelvin. All I have to do is take my temperature, 22.7 degrees, and add 273. So I'd be looking at about 295.7 Kelvin. Fantastic. Then it's just plug and chug. perv-nert is a piece of cake as long as you get the units in properly. That's the only thing I'd just be careful of. And then obviously make sure you pick the right version of R, depending on the pressure unit that you're using. Alrighty, so we plug this all in, and I get, with 3 significant figures, I'm going to say 0.0637, and the unit's going to be liters. When you use the gas constant, all of your other units will match the units of the constant. Cool. All right, so number 4, we're going to calculate the percent hydrogen collected. A percent yield is basically what this is. And that's actual over theoretical times 100. Okay, so the actual always comes from your lab data. So if I go back and look at my data, we collected about 67.20 milliliters. The theoretical is always calculated. If I really produced 0.00251 moles of hydrogen gas, then what should have been the volume? That's just your answer from number 3. But I'm going to switch it so that they're both in the same unit. Now, it really wouldn't matter if you used milliliters or liters. So maybe I'll flip this so that it's like 63.6 milliliters times 100 to make her a percentage. Okay, so I was close. That's actually not too bad, huh? Our data was a little bit high. Okay, so then if I plug this in, I'm looking at about, I don't know, 105-ish%, 106. We'll go somewhere in there. A little bit over 100% yield. So I had a little bit too much gas in that big bubble in the tube. But that's still pretty good. I mean, that's reasonable data. Often in the lab, I say if you're within like 20% of the expected, you're doing pretty good. Now here, this is great. We're only about 5 to 6% off. All right, then moving on to number 5, using the combined gas law. Calculate the volume of hydrogen collected at standard temperature and pressure. Okay, so disclaimer, the combined gas law is not in the equation packet. But don't worry about it. They're not going to have you solve anything with the combined gas law. It's a fine little gas law, and sometimes you use this guy in first year chem, but it will not be on the AP exam. That's fine here. I'll kind of show you what we're trying to accomplish with this guy. Here's what the combined gas law looks like. It's got a little bit of Boyle's law, Charles' law, and Gay-Lussac's law. The whole like P1V1 equals P2V2, that's Boyle's law, the relationship, the inversely proportional relationship between pressure and volume. And then if you look, you can also find like Charles' law was V1 over T1 equals V2 over T2. That's hiding in there. That's the directly proportional relationship between volume and temperature. And same thing, you can also find in there the directly proportional relationship between pressure and temperature. So what we're going to try to do is use this little equation, which again, it's not in the packet and it's okay. You won't have to solve this on the AP test. But I'll show you what we're trying to do with this data. We're going to take P1V1 over T1, and we're going to set that as our lab conditions. And then we're going to make P2V2 over T2 the conditions of STP, standard temperature and pressure. Our lab is not at standard temperature and pressure. But what if it was? Then what volume of hydrogen should I have collected? Here I should have collected about 63.7 milliliters. I actually got about 67 milliliters. What would that be equivalent to if the lab were at standard temperature and pressure? Okay, so we're going to start with our lab conditions. For example, the pressure of the hydrogen gas alone was the 726.06 millimeters of mercury. There's the laboratory pressure of the gas. The volume of gas that I collected in the lab was the 67.20 milliliters. That's what I collected in the lab. And then the temperature in the lab in Kelvin was, up in my perv nerd, 295.7 Kelvin. Whenever you do calculations with gas laws, it's got to be temperature in Kelvin. But volume and temperature are only proportional when you're looking at the temperature in Kelvin. If you double the temperature, you double the volume, but only if you double the Kelvin temperature. And so that's a trick question that they try to give you on a lot of AP tests. Like, what if I go from 20 degrees Celsius to 40 degrees Celsius? What happens to the volume? Well, the volume's going to go up, but it won't double unless your Kelvin temperature doubles. How do we know that? Just by trying it in the lab. If you really had a balloon and you measured its volume at 20 degrees Celsius and 40 degrees Celsius, the volume's going to increase at 40 degrees Celsius, but it just doesn't double. So it's just from lab observations that these variables are only directly proportional, like pressure, temperature, volume, temperature, when the temperature is in Kelvin. All right, so here's all my lab conditions, and now I'm going to set that equal to conditions of STP, which they tell you in the packet. So they'll tell me in the packet that standard temperature and pressure. So we'll go pressure first. They say standard pressure would be 1 atmosphere, but then they also tell you that 1 atmosphere is equivalent to 760 millimeters of mercury. So our lab conditions had a little bit lower pressure. Alrighty, we're going to solve for volume. That's going to be our variable. We want to know, like, what would the volume be under standard temperature and pressure. So then I can just look up standard temperature in my packet, STP. It'll tell me this is 273. Now in the packet it says 273.15, but often you just see 0 degrees Celsius or 273 Kelvin. So yeah, I mean, we're never going to be at like standard temperature in the lab because it's never going to be at 0 degrees Celsius. So I can make some predictions. Like, you know, my lab pressure was a little bit less. My lab temperature was a little bit higher. So if this gas were produced at standard temperature and pressure, well, I mean, at standard temperature, if the temperature is a little lower, then the gas particles would condense a little bit, and I might think that the volume would be a little lower. And same thing, if standard pressure is a little bit higher, that would make the volume a little bit lower. So we plug all this in our calculator and we do some fantastic algebra. And then I'm going to find, let's just do this, that V2 would be about, 59, we'll say 0.27, and that would be milliliters. It's fine to use volume here in liters or milliliters. When you're using PervNert and you've got those constants, then it's gotta be in liters because the constant was measured in liters. Here, as long as the volumes were in the same unit, it doesn't matter. Okay, so yeah, that makes sense. I was expecting a little bit lower pressure, a little bit lower volume at a lower temperature and a higher pressure. So that's the volume that I would expect at standard conditions, standard temperature and pressure. Alrighty, so here then is the moment of truth. Using the volume of hydrogen gas produced at STP, so that's the 59 that I just calculated. Calculate the molar volume of hydrogen at standard temperature and pressure. Molar volume is like the volume of a mole, or it would be in units of like liters per mole. And so we say, all right, well, the volume collected, I had it in milliliters. I'm going to switch it to liters. And I'll say 0.05927 liters. So that was my answer from number 5. That would be the volume of hydrogen I would expect at STP. That's why we had to do that. So like this whole step here is not like in step 5, like that's not always necessary. I mean, often we want to do this type of a lab so we can calculate like moles or volume or something like that using PervNert. Well, here we're just kind of going one step further, and that we're trying to confirm the molar volume of a gas at STP. So I needed my volume at STP. And then that was per how many moles. So then I just go all the way back to number 2 to figure out how many moles of hydrogen were produced. 0.00251 moles. Alrighty, here we go. The molar volume. The volume of 1 mole of any gas at STP. Hey, this isn't too bad. I'm getting 23.6-ish. I'll leave it at that. And that would then be in units of liters per mole. that's not too bad. Because in number 7 then, when they have me calculate a percent error is a little bit different than percent yield. Now we're trying to compare our calculated value to an accepted value. It's actual minus theoretical all over theoretical times 100. All right, so the actual molar volume is what I just calculated, 23.6 liters per mole. Do you remember the theoretical molar volume? The volume of 1 mole of any gas at STP, it's kind of a constant. 22.4 liters per mole. And then I would divide again by the theoretical. 22.4 liters per mole. That's 100. And what do I get here? I don't know. I mean, I'm off by about 5.4-ish%. Somewhere in there. Which is kind of what I expected. I expected to be about 5% off, so that's not too bad. Okay, this number is in the packet. It's in there too. It'll say the ideal gas at STP should have a volume of 22.4 liters per mole. Now here's where it comes from. If you take Herbert,
Appleton North, this is Mr. Pennerberg.
PV equals NRT. Alright, if you take Herbert and you plug in the variables as they would be at standard temperature and pressure, so like for standard pressure, you would have like 760 millimeters of mercury. Let's say you solve for volume, you leave this as your variable. We would be calculating the volume of 1 mole. R would be my constant. And here I would use the constant in whatever pressure unit I chose. So let's say here I'm sticking with the 62.36. And then standard temperature is 273 Kelvin. If you plug all these variables in your calculator, your volume would be 22.4 liters. So it is kind of a constant. It's the volume of 1 mole of any gas. Volume, pressure, it depends on the number of particles, but not necessarily the identity of the particles. So yeah, if you plug all this in, you'll really get about the 22.4. And so we tried to confirm that, and I'd say we were in the ballpark. I'm happy with this. And so then finally, our last 2 questions in the lab. A student noticed an air bubble. An air bubble had leaked into the eudiometer tube when it was inverted into the water bath. So when you flipped it upside down, there was a hole on the end of the stopper. What if a little water leaked out, or you didn't have your stopper in tight? Then obviously you're losing a little water and you're going to have an air pocket in there. What effect would this have on the measured volume of hydrogen gas? Okay, so I've got an air pocket. It might be something like this. Maybe I thought that this volume in here measured to be, we'll say like, I don't know. I think ours was close to, I'll use 67. Ours was close to 67. Let's say we measured 67. But what if there was a little air bubble in there? And so what if, like, up at the top, I have a little air pocket? And so I thought that I had 67 milliliters of hydrogen. But what if I had, like, a little 3 milliliter bubble up there? Well, I did all my calculations assuming that the whole pocket of air and gas up on the top was hydrogen. But what if it wasn't? So in this case, I would have really only had about 64 milliliters of hydrogen, but I didn't know that because I didn't notice, like, oh, whoops, there's already a bubble up there. Oh, man. So it's going to make, then, my measured volume of hydrogen, too low. Oopsies, I should say too high. My measured volume is too high. My measured volume. The actual amount of hydrogen would be less than what I measured. So I thought it was 67 milliliters of hydrogen, but maybe I had like a 3 milliliter air pocket up there. So my measured volume is too high. Which then we sent that measured volume through a series of calculations, and we eventually turned that into a volume that would be present at standard temperature and pressure, and that was then up in here. So if that volume is still too high, does it make sense that my calculated molar volume would also be too high? It seems like I had more hydrogen than what I really did. So all my calculations are going to be a little high, which is probably what happened here. It's hard to flip this thing perfectly, to get the stopper in so that there's no little dribbles, and you want to fill it a little bit over the limit so when you put the stopper in, there's no bubble on the top even to begin with. But sometimes that just happens. It's probably our error here, since our data was about 5% too high. So if we were to run this again, maybe that's something that we would look out for. All right, then finally number 9. A student noticed that the magnesium ribbon appeared oxidized. The metal surface was black and dull rather than shiny and silver. And that is pretty common, that the magnesium is typically a little bit dull and it gets this magnesium oxide coating. Okay, so what effect would that have on the measured volume of hydrogen? And then how would that affect the molar volume? Well, this is going to affect the mass. So we measured 0.061, I think? 0.061 grams of magnesium. But I tried to clean mine really well, which hopefully we did an okay job. But if you didn't clean it, then part of that mass is not just magnesium. Part of that mass might be magnesium oxide, which is what I tried to remove. The magnesium oxide doesn't react with the hydrochloric acid in the exact same way as just pure magnesium. It's not going to produce hydrogen gas. It just adds mass. And so really then, if my mass, my mass of measured magnesium is really too high. So if my mass is too high, because maybe that's not all magnesium anymore, my mass is too high, which means my moles will be too high. Well, right there I can answer the second part, because when we were doing this calculation for molar volume, it was liters per mole. Well, now if my moles is in the denominator and that value is too high, it should make my calculated molar volume too low. Well, then what effect would this error have on the measured volume of hydrogen gas? That will also be too low. Or I could say lower than expected. Because I'm expecting that 0.061 grams to be all magnesium, and if I turn that into moles, it should give me the exact same moles of hydrogen gas. But really now, part of that mass wasn't really magnesium. So part of that mass is not going to be converted into hydrogen. So then the volume that I measure would be lower than I expected. And same thing, my calculated molar volume would also be too low. All right, so we're going to offer a couple sentences for maybe questions 8 and 9 to explain how those errors would affect our data, and then a quick and easy conclusion. Here we're going to just kind of summarize the purpose of the lab. We were trying to prove the molar volume of a gas at standard temperature and pressure. We can discuss our percent yield of hydrogen or our percent error with the molar volume. They're really going to lead us in the same direction. In this case, our data was a little bit too high. So what might be some logical sources of error, which obviously now we can kind of look at questions 8 and 9, and then maybe what could we do differently? If we could run this procedure again, what should I have done differently, or what could I do better to hopefully prevent those errors in the future? When you're done then, and you can write all of these calculations on a sheet of scratch paper, just upload photos of your work and submit the document, and the lab is all set.